All right. Hi, everyone. My name is Charles Averill. I'll be teaching the Practical Compiler Design Workshop this upcoming spring at the University of Texas at Dallas. And let's go over some prerequisites that will help you throughout this course. So these are the 5 big ones. The first thing is that you need to be experienced in an imperative programming language. Those are all the popular ones that you've probably heard of: C, C++, Java, Python, JavaScript, stuff like that. This course will be taught in Python. I'm providing a project base, and that's going to be in Python. And so I would encourage that you have familiarity with Python at least. However, if you're confident in another language, that's going to be fine. I'm not really going to be using any specific Python features. I'm staying away from any kind of class workings and so as long as you can translate, loops and functions and stuff like that to whatever language you'd like to program in, that will be fine. You need to know a little bit of assembly language programming. It doesn't really matter which assembly language. You need to know about trees, linked lists, hash tables, and tree traversal. And really the bare minimum for all of those. You don't need to be an expert or anything. And then you should be at least somewhat familiar with Unix and Bash. So the project base is assuming that you're running it on a Linux machine. So if you're at UT Dallas, then you can use the CS1 server that we have, or use a physical Linux machine. I am providing a Docker file, but it's just better if you use Linux. And then knowledge of Git. So all of our class submissions are going to be done through GitHub or GitLab, whichever you prefer. And so yeah, let's get into the specifics of each of these. So with imperative programming, unfortunately, I can't really give any kind of succinct tutorial on how to learn that. That's something that hopefully you've been doing for a while. This class is marketed towards junior and senior level students, so you should be very familiar with imperative programming. However, like I said before, any programming language that follows those paradigms is going to be fine. Specifically, it needs to have conditional statements like if. It needs to have loops, while and for, functions, and simple classes. I say simple classes because C has structs, and those are just fine. Just any kind of data container like that is fine. As long as your language supports that, you'll be good. Our project base is called Echo. It stands for Educational C Compiler. So if you're going to follow along with the project base, and you don't have to, if you are though, you should be familiar with the C programming language because it's a C compiler written in Python. So I picked C because it's fairly simple, believe it or not. I know a lot of people don't agree with that, but the language itself does not have many features. And the only thing that I would really consider esoteric about C is pointers and macros. Pointers, you should look up a tutorial if you're not familiar with those at this point. But there's not much that you'll need to worry about there. And also, pointers come along pretty late in the class. So if you're just following along with the Echo compiler, you won't need to know about pointers for a while. And the same thing with macros. They're going to show up about halfway through. And if you want to learn about those, any online tutorial, again, you don't have to be an expert. Just be comfortable. And I'll cover some Python syntax real quick if for some reason you haven't seen any. So this first little block right here, we've got conditional statements and logical operators. So this is our if statement. If the condition that follows the word if is true, then it will execute the indented code. So those light blue highlighted things, those are conditions. Those are statements that evaluate to true or false. and then you see and, or, and not. And, or, and not are all logical operators. And and or are binary logical operators, so they take two conditional statements or conditional phrases, I guess you could say. And so that's going to evaluate to true if and only if the conditions on either side of it are true. For or, it just has to be one of them. And then not is a unary operator, so that's just going to invert whatever condition 4 is here. In our next block, we've got some loops, and these are both, even though they're written different, they both have the same behavior. So this is our for loop at first. We see for I in range. Python does not have standard for loops. Instead, it will give you a range object or enumerator, and that kind of acts like a list that you can pull items from. And so the range object is going to basically give you the numbers 0 through 9 one at a time, and so it's going to print out I at each step. And then we've got our while loop, which again does the exact same thing, where we set a counter x to 0, and then as long as x is less than 10, we're going to print it out, and then we're going to increment it. So, and here's some function syntax. The def keyword is how we define a function header. We're going to call this one dot prod, short for dot product of two vectors. And so inside of the parentheses, we have the parameters to the function. You'll notice I've got these colons and then these type names everywhere. These are called static type hints. It's not something that you see a lot in Python code. And the reason for that is because it's really just decoration, and it doesn't have any effect on the interpreter itself. So what it's saying is it's hinting to you that you should pass in a tuple that contains two integers for u and for v. However, you don't have to pass in a tuple with two integers. You could pass a list, or you could pass anything in, and if you pass in the wrong object, it's just going to return an error. So I will use type hinting frequently. In fact, I mean, there's really no time I'll ever not use type hinting whenever I am writing the echo compiler. So you're going to see a lot of that, and you're going to get very used to it. So this function only has one statement, a return statement, and it's going to return the product, or the sum of the products of the pairs in these two tuples. So we're going to multiply the first item in u and the first item in v, and then we're going to add that to the product of the first item, or the second item in u and the second item in v. So that's list accesses and some multiplication and addition for you. And then the second, that was just the definition of the function. The second statement here is a print statement. It's just going to print out the dot product of the vector 1, 2 and the vector 3, 4. And that's, the answer for that is 11, if you recall from any physics class. Here is a class definition in Python. So I said I'm not going to use any specific Python features, but I do use a few classes. Again, those aren't Python specific, but if you're writing your compiler in C, you are going to have to do a fair amount of translation there. But we've got a constructor. Again, that's a method, so we use the def keyword, and then we have this dunder in it. That's what we call the two underscores on either side of the init. This is a special function name, and it just tells Python that this is the constructor. And so, for example, this is a dog class, and so it's going to take in a name, a breed, and an age. And we're just going to set those values with the self keyword. Don't worry about why there's self at the beginning of every function. Just do it. That's what Python wants you to do. You don't have to, but we don't really need to get into static methods here. And then we've got a class method called speak, and it's just going to print out bark, I am, and then it will follow with the name of that dog instance. So we've got, this is outside the scope. Python is all about indentation, so outside of that scope, we've got Beth equals dog, Beth Golden Doberman 3. And so that's saying, give me a dog object with a name Beth, the breed Golden Doberman, and the age of 3. And then give this object the identifier Beth with a lowercase b. And then we're going to say Beth.speak, which calls that class method, and it's going to print out bark I'm Beth. Okay, so that's enough of Python. Let's talk about assembly programming. So Echo is going to compile C source code to LLVM-IR. LLVM-IR is a pseudo-assembly language that can be compiled into real assembly languages like x86, ARM, MIPS, etc. And it can also be optimized usually by the Clang compiler. It's not optimized by the Clang compiler, it's optimized by a chunk of the Clang compiler, but same difference. It's very, very different from the common assembly languages. However, it is grounded in the same concepts, which are registers, instructions, jumps, and stack memory. So let's talk about registers. Registers are tiny little spaces on CPUs. They're usually less than 100 bits. Your standard desktop at this point in time is probably going to be a 64-bit register. Maybe some 32s in there, but they're tiny little spaces directly on the CPU chip, and they store data for the CPU to operate on. They're very tiny, and there's not very many of them because the more you make, the slower your operations become as they retrieve data that is physically farther away from the arithmetic unit or whatever on your CPU. So they're just enough space to store a character or a number or something like that, or a pointer to something. Some registers are general purpose, so they can just be used to hold any data that a programmer or compiler wants it to hold. However, some registers are a specific purpose. So in MIPS, the 0 register, and in MIPS we denote registers with a $sign like that. 0 register is a read-only register that always contains the number 0. So you can't overwrite it. You can basically just copy the number 0 from it. There's really not many other uses. Most architectures, probably all architectures, have a program counter register that basically holds the offset of the current instruction of whatever program is being run. And then the stack pointer is a register that will hold on to the address of the next free space on the stack, and we'll talk about that in a second. Okay, so the next thing, let's talk about instructions. So, in our high-level languages like Python, Java, etc., we have keywords like if and while and def and function and class and all those things. And they all have fairly complex meanings. Maybe you don't consider if to be a very complex keyword, but it's definitely not a, it's not a fundamental operation on the CPU level. Same thing with for loops or classes or anything like that. Those are all very abstracted away from what the CPU is actually doing. So assembly languages are the opposite. They have lots of small instructions with keywords attached to them to denote a very small operation on data, usually something very fundamental. CPUs, assemblies, languages, they usually don't support any high-level structures like classes or structures or anything, structs or anything like that. So, for example, we've got the instruction sub-u, which stands for subtract unsigned, or BNE, which stands for branch if not equal in MIPS. Instructions are usually going to take registers and or constant values as input and output arguments. For example, If we have an add instruction, it's going to take in 3 input arguments. And for this one example, we've got R2, R1, R3. And what this translates to is add the contents of registers 1 and 3 and then store them into the register R2, or store the sum of those 2 registers into R2. In MIPS, we have add I, which is short for add immediate, and it's going to take in 3 values again. However, the third one is going to be a constant value. In this case, it's 64. And so what this is saying is that we're going to take the contents of register T1, we're going to add 64, and then we're going to store the sum in register T2. All right, so in high-level programming, we are very familiar with stuff like loops or if-else statements. These are actually just abstractions that can be reduced to what we call conditional jumps or branches once we get to the CPU level. So the following code samples in Python and MIPS are equivalent. So we've got if x is greater than 100, x equals 0, else x equals 50. And those are, assignment statements. We're going to set x equal to 0, or we're going to set x equal to 50. And so we can see in the MIPS block that register T0 contains the value for x, and register T1 contains the value 100. So this first instruction, this is pretty common in assembly. If-else statements are kind of reversed. So we're actually going to check the converse of the condition that we're concerned about. So we want to check if x is greater than 100, but we want to save a jump. We don't want to do any more jumps than we have to because they're kind of slow. So we are going to check the opposite. We're going to actually check if x is less than or equal to 100, which is going to produce the opposite result of x is greater than 100. And if that is true, then we're going to branch to the false clause, which is our else statement up above. And you can see that we're going to call this li function right underneath the false clause identifier. We're gonna call this li, which stands for load immediate, which basically says copy this constant value into this register. So here we're copying 50 into T0, which we said was x. So this is kind of like setting x to 0. And then after that li executes, it's going to go right to that end clause. So that's only if x is less than or equal to 100. But if x is greater than 100, that BLE, the branch if less than or equal to, that's going to return false, so it's not going to branch. So instead it's going to fall through to this true clause, which is what would happen if x was greater than 100. And so we're going to load immediate, and we're going to load 0 into T0, which is, again, kind of like setting x to 0. And then we've got this J end clause. And so that's going to jump to this end clause, and it's going to skip that false clause because we don't want both to happen. We only want one of them to happen. So that's a little bit about jumps. All right, so jumps are also how loops work. Again, here's a Python statement, Python block on the left, and here's a MIPS block on the right, and they are functionally equivalent. So we're going to set a value x to 0, and then for every number in the range 0 through 9, we're going to set x equal to that value. And so this kind of really doesn't do anything but set x to 9 in a more complicated way, but it's just, let's look at how it translates to assembly. So again, over here on the right, we have the register T0 contains the value for x, T1 contains the value for I, and T2 is going to be the value 10. So the first thing that we're going to do is we're going to load immediate. We're going to load the values 0 into both x and I. So for x, that's pretty obvious on both the for and the while loop. However, with I, on the for loop, remember that range is an enumerator that gives you basically a list of the numbers 0 through 9, at least when you plug 10 into it. Gives you 0 through 9, and then it feeds those to you one at a time. So the first value is 0, so that's what we're going to load into the I register. So after doing that, we're going to go into this loop head block. And so the first thing we're going to do is we're going to move the contents of T1 into the contents of T0. So that's actually a copy. It's not like it erases the value of T1 afterwards. But that is our assignment statement that we see in both loops where we set x equal to I. Because remember, T1 is I, T0 is x, so it makes sense. The next thing we're going to do is we're going to add 1 to I. That's what that add I, remember? That's add immediate. It's just going to add 1 to whatever register you give it. So it's going to add 1 to T1, which is I. And you see that in the while loop, and then functionally that makes sense in the for loop. And then we have another branch statement. This one says branch if less than, and it gives us the registers T1 and T2. So it's saying if I is less than 10, then jump to loop head. And so again, this makes a lot of sense for the while loop, and if you think about it a little bit, it should make sense for the for loop as well. And then, once I equals 10, it's not going to branch, and then it's going to fall through to whatever code comes after. So, all right, so let's talk about stack memory. So CPUs usually have this register called the stack pointer that we talked about, which is going to point to the expanding end of stack memory and RAM. And that means that whichever end is free, whichever end you can add more contents to, that's what it's going to point to. And whenever we have data that is too big to fit into a register, it ends up on the stack. Or it ends up in the heap, but we're not going to be talking about the heap right now. So in a high-level language, when functions are called inside of each other, so if you write two functions and you call one inside of the other, then what's going to happen is that when the outer function is executing and it reaches another function call, the first thing that it's going to do is it's going to take all of the register contents that it needs to resume that function later, and it's going to push it onto stack memory so that when it goes into the newly called function, it can use all those register spaces without worrying about overwriting any of the important data that happened, that was being interacted with before the inner function call happened. So whenever the child function terminates, the outer function is going to pop the data back from the stack. It's going to remove the data back from the stack, and it's going to pop it back into the appropriate registers. And by doing this, we can have a very large amount of functions call each other. At worst, we can do it until stack memory runs out, but I think most modern languages these days have, they'll stop you from running out of stack memory. There'll be some limit. And most of them have, for example, a recursion depth limit, and that's fairly obvious because most recursive calls shouldn't go on too long. But anyways, so let's get on to the data structures that we need to understand all of the components of the compiler that we're going to build. So the first one's really easy, linked lists. So a linked list is a often / usually bidirectional network. Sometimes it is in one direction, but that's not a big deal. And it's a network in which each node has exactly 0 or 1 child nodes, which we call successors, and exactly 0 or 1 parent nodes, which we might call ancestors. So we can see in this diagram here that the 4 node has 1 child, which we can say is 3, and it also has 1 parent or ancestor, which we call 5. But 5 is not the parent of all of these. It's the grandparent of 3 and the great-grandparent of 2, but the whole point is that it's a list. So it's just a kind of flat data structure that we can store things in to represent an order. And then we're usually going to have a head pointer that points to whichever object is the front of the list. Sometimes we might have a tail that points to the back of the list, but that's not super important because whichever object is at the head, if it's a doubly linked list, then it's going to be able to point back to the tail. So that's a linked list. Let's get into trees. So a tree is an oriented network. It can be bidirectional, usually. I use usually because in the context of our compiler, the Echo compiler, it is usually bidirectional. And it's also hierarchical. It's those things that consist of this network of parent and child nodes. And what that means is that there's a set of nodes, some of whom are parents of multiple other nodes. And a node can only be the child of one parent, has to have one parent, except for the root of the tree. So in this image right here, we've got a ternary tree, which means that at most each node can have up to 3 children, or up to and including. It can have 0, 1, 2, or 3 children. And so this 10 node, that is our root. So it's the only node in the network that does not have a parent. And it has 3 children. It has 85, 30, and 7. 7 does not have any children, while 85 and 30 both have children. We call 7 a leaf because it does not have any children. And for the same reason, all of these 6 at the bottom, these are also leaves. And let's talk about how to traverse a tree. This is super, super, super important. The compilers for most of your imperative languages are going to heavily rely on recursive tree traversal to do so many things that we'll find out about this semester. And so let's talk about traversal. Traversal of a tree describes a set of algorithms, because there's many ways to do it. A set of algorithms that move around the tree and perform operations using the data at each node, and they also use the relations between the nodes. And for our cases, traversal algorithms are going to visit every node in the tree. Some don't. A search algorithm often, most of the time won't visit every node in the tree, but for this case, it will visit every node in the tree. So the two big ones are breadth-first traversal, which we call BFS for short, and depth-first traversal, which we call DFS. And so breadth-first, it seems pretty self-explanatory. It's going to spread out from the top, so it's going to check layer by layer, basically. Not exactly, but it's just going to spread out instead of pinpointing, which is where the depth-first traversal is going to go to each node. It's going to go to the deepest node possible at any given time. So the depth-first traversal, these say BFS and DFS. They should be BFT and DFT. I put S there for search instead of traversal. That was an accident. But the depth-first traversal of the image below, of the tree in this image, is going to be 10, and then 85, and then 31. And that makes sense. It went to the deepest ones first, and we kind of arbitrarily picked the left direction to go in. But now that we've reached the deepest, we're going to go back up, and then we're going to go down to 15. So it's going to say 31, and then 15, and then 40. And then again, we're going to go, Again, we're going to go back up. We're going to go back down to the next deepest, which is 30. And then we're going to go to 63, 1, 15, and then back up, and then down to 7. And there we go. We've traversed every node in the tree. And then the breadth-first traversal of the below image is going to be 10, and then it's going to hit 85, 30, and 7. And then it's going to hit 31, 15, 40, and then 63, 1, 15. Okay, let's talk about hash tables. So hash tables are one of the, more complicated data structures. Definitely not the most, but they're up there. And so a hash table is a key value structure. And that means that any value that you want to put into the network or the table is going to be represented by a key. It could be a number, it could be a string, it could be anything really. And these keys are going to be passed through a hash function, which is one way you could describe it is that a hash function is a one-way encryption scheme, which means that once you hash your data, it's very hard to unhash it, which is important for a lot of security reasons, but we're not concerned with security here. We're using a hash function because it can take in various kinds of data, and it can output an integer, any kind of whole number that represents the row index of corresponding data, the values in the table. So we're going to pass a key that represents our value. We're going to pass the key through the hash function, and it's going to spit out an index in our table where we can put that value. And that way we can pass that key through the same hash function over and over, and we always get the same index. And so this makes it very fast to look things up because you don't have to traverse the entire table. You just hash the some corresponding data that goes with your value, and it'll give you an index. And so that's depending on how fast your hash function is. It's a very fast access. And these values can actually be any kind of data, including a linked list. This is something that we're going to utilize later. Instead of just putting raw data into our values, we're going to put linked lists of things into our values. Okay, so let's talk about basic Unix and Bash usage. So again, you should know the very basics of Unix usage, so just how to run Bash scripts. If you don't know that, I suggest there's plenty of videos online, but I'm just covering what you should know. So our Echo project base is going to have a scripts file, which is a Bash script, and it's going to take in some arguments to perform different actions. For example, if you run scripts run test file, it's going to start up our compiler, it's going to pass our test file into it, and then it's going to execute the generated assembly code that comes out of the compiler. Scripts all test file is going to format and lint your compiler source code, and then it's going to compile and execute test file again. So if you do not have access to a Unix or Linux-based machine, again, you do if you're a UTD student, I expect that you understand Docker well enough to use the provided Docker file in a Windows environment, or I expect that you can set up WSL, which is the Windows subsystem for Linux, and use it to execute all of your code. If you're stubborn and you really want to do this on Windows, you have to know one of those two things, Docker or WSL. I'm not going to be covering those because I don't use Windows, so I'm not sure how either of those things really works in Windows. I've used Docker plenty of times on Linux, and at least on my Linux machine, the Docker file does function properly. So hopefully that will be sufficient for you to run your code in your desired environment. Okay, and so the last thing that we're going to cover is Git usage. So if this is your first time ever using Git, I'm very excited to welcome you into the next phase of your career as a software developer. In my opinion, Git is probably the most impactful software development tool since basically the first text editor or the first operating system was ever designed. It is a versioning system which allows you to track changes that you make in your source code over time. This is really helpful if you make a mistake and you forget how you got that mistake and you need to revert to an older version of your code that does work. Or you can look at where you introduced a bug in the past that you didn't notice until some point in the future. Another thing about Git is that it is collaborative, so you can work with multiple people and you can merge your code together. We're not going to get into that because this is not a group project class. So we're going to cover the basics of Git usage, although I do suggest that you look at a tutorial if this is completely new to you, because this is going to be a very cursory Git tutorial. Basically, Git is going to have this thing called a working directory, which in terms of the Echo compiler is going to be the compiler source code and some configuration files that go with it. It's literally just the directory that the code lives in. So any changes that you perform in the working directory are temporary and can be reverted after, as long as you dismiss the warning that Git gives you. The staging area is where you're going to temporarily put your changes to your working directory when you're almost ready to kind of cement them in your Git repo history. This is accomplished by running the command git add and then followed by a list of any of the file names that you want to record changes for. And you're just going to separate those by spaces. And when you're ready to kind of cement your changes in history, you can run git commit -m or tac m, and then you're going to put a descriptive message of all your changes. These are going to add your changes to the committed files area of the repository. And I said kind of cemented because you can alter commits after running git commit, but I would consider it to be non-trivial. So you can kind of treat this as a permanent action for many intents and purposes. So one thing is that these commit messages, I do expect that y'all will write descriptive ones that outline at least the major changes. You don't have to document every single line of code that you changed, but I do want to see a descriptive message because I like knowing what changed, and I don't want to have to dig through every line of source code change. So next thing is remote Git usage. So this is the last thing we're going to talk about today. Sometimes you want to back up your Git repository to an external server in case you drop your laptop in some water or something. Or maybe you want to collaborate with other people on the internet. In these cases, you can use a service like GitHub or GitLab. These websites are going to let you remotely host Git repositories. And so if there are local changes to your Git code that you want to add to the remote repository, and this is after you've run git commit, you can run git push origin main. Origin and main are tentative because origin is just kind of the standard default pseudonym for any remote server that hosts a Git instance. You don't have to, you don't have to call your remote origin, but I just suggest that you do because that's what everyone calls it. And then main here is the name of a branch. So branches are how we do collaboration in Git, or how we work on individual features instead of messing with all of our code at the same time. And so Git lets you split your development across multiple versions at the same time, and that's what we call a branch. It's just one version. And later on, once, for example, you might make a new branch to work on a single new feature, and then you can merge it back together into the main copy of the code. You can merge multiple things. You can have as many branches as many branches as you want at any given time, and you can merge them when you see fit. And this is very helpful, so that multiple people can work on different parts of software in tandem and then combine their work with, I'm not going to say easy because it is fairly complicated sometimes, but it is certainly deterministic. It is a deterministic way to resolve any conflicting changes. If two people made changes to the same line, that's a conflict, and you're going to need to resolve those before you can continue merging your code. However, in my opinion, you will not really need to work on multiple branches because we're going to be taking a very linear approach to how we're designing the compiler. So that is the conclusion of all the prerequisites that you might need to know for this course. Thank you for tuning in. If you have any questions, you can email me or message me on Discord. So that's it. Thank you very much.